Welcome to Gas Hydrates and Gas Dehydration. In this course, we will explore one of the most important flow assurance challenges in the natural gas industry, the presence of water. Water may appear harmless, but under the right conditions it can lead to hydrate formation, pipeline blockages, corrosion, operational disruptions, and significant economic losses. We will begin by understanding how hydrates form and why they pose such a serious risk. We will then examine the most common prevention methods used in industry, including methanol and glycol injection systems. Next, we will study gas dehydration technologies, with a strong focus on TEG dehydration systems, which are widely used to remove water and meet pipeline specifications. Finally, we will apply these concepts through practical engineering examples and real-world field scenarios. By the end of this course, you will be able to identify hydrate risks, evaluate mitigation options, and understand how dehydration systems support safe and reliable gas production. Before we start the technical details, let's look at the complete flow assurance journey covered in this course. Everything starts with natural gas produced from the reservoir. As gas flows through production and transportation systems, water is often present. Under the right combination of pressure and temperature, this water can combine with natural gas molecules to form gas hydrates, ice-like crystalline solids capable of restricting or completely blocking flow. To manage this risk, engineers apply hydrate prevention techniques such as temperature control, pressure management, and chemical inhibitors like methanol or MEG. However, the most effective long-term strategy is often gas dehydration, removing water from the gas stream before hydrates can form. Before discussing hydrates, we need to understand why water is such an important concern in natural gas operations. Water is naturally produced from many gas reservoirs and is often present as vapor or free liquid throughout the production system. As gas flows from the reservoir to processing facilities and pipelines, pressure and temperature conditions continuously change. These changes can cause water to condense and create conditions that favor hydrate formation. Water can also contribute to corrosion, liquid accumulation, operational instability, and reduced gas quality. One of the most important concepts in gas processing is the dew point. When gas cools below its dew point, water begins to condense from the gas phase. For this reason, controlling and removing water is a fundamental requirement for safe, reliable, and efficient gas transportation. So what exactly are gas hydrates? Gas hydrates are ice-like crystalline solids formed when water molecules create cage-like structures that trap natural gas molecules. Although they look similar to ice, hydrates are fundamentally different. Ice is simply frozen water, while hydrates contain both water and gas trapped within a solid crystal structure. Methane is the most common gas found in hydrates, but other hydrocarbons and gases such as carbon dioxide and hydrogen sulfide can also participate in hydrate formation. Hydrates can form very quickly when the right pressure and temperature conditions exist. Once formed, they can grow rapidly and accumulate inside pipelines, flow lines, valves, and production equipment, creating one of the most serious flow assurance challenges in the gas industry. Hydrate formation requires 4 key conditions to exist at the same time. First, water must be present, either as liquid water or water vapor. Second, natural gas must be available to occupy the cages formed by water molecules. Third, pressure must be sufficiently high to stabilize the hydrate structure. And fourth, temperature must be low enough to favor hydrate stability. When these 4 conditions occur together, hydrate crystals can begin to nucleate and grow. The important engineering principle is that hydrates cannot form if any one of these conditions is removed or controlled. This is the foundation of all hydrate management strategies. Engineers prevent hydrates by removing water through dehydration, increasing temperature, reducing pressure, or injecting inhibitors such as methanol or MEG. Every hydrate prevention method is ultimately based on disrupting one or more of these 4 requirements. Hydrate formation depends strongly on pressure and temperature. As pressure increases, hydrates can form at higher temperatures. As temperature decreases, hydrate risk increases significantly. The hydrate stability envelope defines the conditions where hydrates are thermodynamically stable. Engineers use these diagrams to evaluate operating risk and determine whether prevention measures are required. The objective is to keep the operating point outside the hydrate stability region whenever possible. Hydrates can form almost anywhere in the gas production system where water, gas, pressure, and low temperature exist together. The highest risk locations are typically wellheads, chokes, flow lines, subsea pipelines, separators, and long transmission pipelines. As gas travels from the reservoir to processing facilities, pressure and temperature continuously change. These changes can create ideal conditions for hydrate formation. Subsea systems are particularly vulnerable because of the cold surrounding seawater. Even onshore pipelines can experience hydrate problems during winter conditions or rapid pressure reductions. Understanding where hydrates are most likely to form allows engineers to place monitoring systems, dehydration units, and chemical injection points at the most effective locations. Hydrate management begins with identifying the highest risk sections of the production system. A few drops of water may not seem important in a gas pipeline, but under the right conditions, they can stop millions of dollars of production. Gas hydrates form when four factors come together. Free water is present, temperatures are low, pressures are high, and the gas composition supports hydrate stability. When these conditions exist, ice-like hydrate crystals can grow inside pipelines and equipment. As shown in the center of the slide, these crystals can accumulate into a hydrate plug, restricting flow and potentially causing a complete shutdown. The operational impacts are significant: reduced production, unplanned downtime, equipment damage from pressure buildup, and increased operating costs. To prevent hydrates, engineers use a combination of strategies, including methanol or MEG injection, gas dehydration to remove water, temperature control, pressure management, and continuous monitoring of operating conditions. The engineering lesson is clear: hydrates are predictable. If we control the conditions that create them, we can protect production, improve reliability, and avoid costly interventions. A few minutes ago, we learned how hydrates form. The next question is simple: how do we stop them? In industry, there are three primary hydrate prevention approaches, and the right choice depends on operating conditions, economics, and risk tolerance. The first method is inhibitor injection, typically using methanol or MEG. These chemicals lower the hydrate formation temperature, making them highly effective for startups, shutdowns, and emergency situations. The second method is dehydration, most commonly using TEG systems. By removing water vapor from the gas stream, dehydration eliminates one of the essential ingredients required for hydrate formation. This is often the preferred long-term solution for continuous operations. The third approach is operational control. By managing pressure and temperature, applying insulation or heat tracing, and continuously monitoring operating conditions, engineers can keep the system outside the hydrate formation region. Successful hydrate management rarely relies on a single technique. The best results come from understanding the system, monitoring performance, implementing preventive measures early, and combining methods when necessary. The engineering principle is straightforward. There is no one-size-fits-all solution. The most effective strategy is the one that matches your operating conditions while delivering safe, reliable, and efficient operations. Hydrate formation is more than a flow assurance issue. It can become a major operational and safety challenge. As hydrates begin to accumulate, they restrict the available flow area inside pipelines and equipment. This restriction increases pressure losses and reduces production rates. If hydrate growth continues, a complete blockage can occur. Such blockages may force operators to shut down wells, flow lines, or processing facilities. Hydrate plugs can also create dangerous pressure buildup. Removing them often requires expensive intervention and extended downtime. The cost of prevention is typically far lower than the cost of remediation. For this reason, proactive hydrate management is considered a critical part of safe and reliable gas operations. The hydrate phase envelope is one of the most important tools in flow assurance because it helps us predict where hydrates can form and how to avoid them. The process begins by defining the system, including gas composition, water content, salinity, and inhibitor concentration. We then select a suitable thermodynamic model and generate pressure-temperature data to determine hydrate formation conditions. These points are plotted to create the hydrate phase envelope. The curve divides the operating space into two regions: a hydrate stable region, where hydrates can form, and a hydrate unstable region, where hydrate formation is not expected. Before using the envelope, it should be validated against field observations or laboratory data, and an operating margin should be established to provide a safe buffer from the hydrate boundary. Once developed, the envelope becomes a powerful decision-making tool. Dehydration reduces water content, inhibitor injection shifts the hydrate boundary, temperature control keeps operations above hydrate formation temperatures, and pressure management keeps conditions outside the hydrate region. Combined with real-time monitoring, these strategies provide multiple layers of protection against hydrate formation. The engineering lesson is clear. A well-constructed hydrate phase envelope helps engineers understand risk, select the right mitigation strategy, and operate safely and reliably. No single hydrate prevention method is ideal for every application. Heating systems can be effective but often involve significant energy consumption. Pressure reduction may eliminate hydrate risk, but it can also reduce production performance. Methanol offers rapid protection and operational flexibility, but chemical costs can be high. MEG provides long-term protection and recovery benefits but requires more complex facilities. Dehydration removes water from the gas stream and addresses hydrate formation at its source. Engineers evaluate technical performance, operating costs, reliability, and field conditions before selecting the most appropriate solution. The best solution is often a combination of several methods working together. These chemicals do not remove water from the gas stream. Instead, they change the conditions required for hydrate formation. By lowering the hydrate formation temperature, inhibitors allow the system to operate safely at conditions that would otherwise promote hydrate growth. The two most common thermodynamic inhibitors are methanol and monoethylene glycol, commonly known as MEG. Methanol is typically used for short-term or emergency protection, while MEG is often selected for continuous operations because it can be recovered and reused. The selection depends on operating conditions, economics, and facility design. Methanol injection provides one of the fastest methods for hydrate prevention. The system is relatively simple and consists of a storage tank, injection pumps, and injection points located at critical locations in the process. Once injected, methanol mixes with the water phase and reduces the temperature at which hydrates can form. Because of its rapid response, methanol is commonly used during startups, shutdowns, well testing, and emergency situations. However, methanol is generally not recovered after use. This can result in significant operating costs for continuous applications. For this reason, methanol is often viewed as a flexible short-term solution rather than a permanent hydrate management strategy. MEG systems provide long-term hydrate protection in many offshore and subsea developments. Like methanol, MEG shifts hydrate formation conditions and reduces hydrate risk. However, the major advantage of MEG is that it can be recovered and regenerated. After injection, the rich glycol stream is collected, processed, and regenerated before being returned to the system. This recovery loop significantly reduces chemical consumption and operating costs. Although MEG systems require more equipment and higher capital investment, they are often the preferred solution for large-scale continuous operations. Many modern subsea developments rely heavily on MEG as a key flow assurance strategy. Gas dehydration is one of the most important operations in gas processing. The objective is simple: remove water from the gas stream before transportation or further processing. Water in natural gas can cause hydrate formation, internal corrosion, liquid accumulation, and operational instability. In addition, sales gas must meet strict water content specifications before entering transmission pipelines. By reducing water content, dehydration improves flow assurance, protects equipment, and ensures compliance with commercial gas quality requirements. For many facilities, dehydration represents the first line of defense against hydrate-related problems. Hydrate prevention is not a one-time activity. It's a continuous management process that evolves throughout the life of an asset. This slide illustrates the hydrate management cycle, a structured approach used to maintain safe, reliable, and efficient operations. The process begins with assessing risk. Engineers evaluate operating conditions, fluid properties, and the likelihood of hydrate formation. Once the risk is understood, the next step is selecting the most appropriate solution, whether that's inhibitor injection, dehydration, operational controls, or a combination of methods. After implementation, performance must be continuously monitored. Key parameters such as pressure, temperature, water content, and inhibitor dosage help verify that the chosen strategy remains effective. The results are then reviewed and optimized. As operating conditions change, prevention strategies may need adjustment to maintain performance and control costs. This cycle of assessment, implementation, monitoring, and improvement creates continuous protection and maximum uptime. The benefits extend beyond hydrate prevention. They include reduced downtime, protected equipment, lower operating costs, improved reliability, and more sustainable operations. The engineering principle is simple. The most successful hydrate management programs are not reactive. They continuously adapt, improve, and evolve with the operation. Successful hydrate management is not about reacting to problems. It's about building a disciplined process that prevents problems from occurring in the first place. Everything starts with understanding the foundation of hydrate formation: water, low temperature, high pressure, and hydrate-forming gases. Once these conditions are understood, engineers can develop an effective prevention strategy. The best practice framework shown here follows 6 key steps. First, assess and plan by evaluating risks and selecting the right strategy. Next, prevent hydrate formation using methods such as dehydration, inhibitor injection, or operating controls. Then monitor critical parameters and respond quickly to any deviations before they become operational issues. The process continues with verification of results and ongoing improvement through performance analysis and optimization. This creates a cycle of continuous improvement rather than a one-time solution. However, technology alone is not enough. Long-term success depends on skilled people, reliable technology, quality data, standardized processes, and strong partnerships across the organization. When these best practices are applied consistently, the rewards are significant: safer operations, higher uptime, lower costs, better asset protection, and sustainable long-term value. The bottom line is simple. Great hydrate management is proactive, integrated, and continuous. The goal is not just to prevent hydrates today, but to build reliable operations for the future. TEG dehydration is the industry standard for water removal from natural gas. The process begins in the contactor tower, where wet gas flows upward while lean TEG flows downward. As the gas and glycol come into contact, water transfers from the gas phase into the glycol. The dry gas exits the top of the tower and proceeds to downstream facilities. The water-rich glycol then flows to the regeneration section, where the absorbed water is removed. The regenerated lean glycol is recycled back to the contactor, creating a continuous dehydration cycle. This process provides efficient water removal and reliable operation across a wide range of gas processing applications. The contactor tower is the heart of the dehydration system. Wet gas enters near the bottom while lean glycol enters from the top. As the two streams move in opposite directions, water vapor transfers from the gas phase into the glycol. The effectiveness of this process depends on pressure, temperature, contact area, and glycol quality. The result is a dry gas stream leaving the top of the tower and a water-rich glycol stream leaving the bottom. After absorbing water in the contactor, the glycol must be regenerated before it can be reused. The rich glycol is heated in a reboiler, causing water to vaporize and separate from the glycol. Once regenerated, the lean glycol is cooled and returned to the contactor. Efficient regeneration is essential because glycol purity directly influences dehydration performance. This closed-loop process allows continuous operation while minimizing chemical consumption. Some gas processing applications require extremely dry gas that exceeds the capability of glycol systems. In these cases, solid desiccants such as molecular sieves are used. The desiccant adsorbs water from the gas stream and retains it within its porous structure. When saturation occurs, the vessel is regenerated using heated gas. Multiple vessels operate in alternating cycles to provide continuous dehydration. This technology is widely used in LNG and cryogenic processing facilities. Selecting a dehydration technology requires balancing technical requirements with economic considerations. TEG systems are generally preferred for conventional gas dehydration because they provide reliable performance at reasonable cost. When extremely low dew points are required, molecular sieve systems become necessary. Engineers must evaluate gas flow rate, operating conditions, water content, reliability, and life cycle cost before making a selection. The optimal solution is the one that satisfies process requirements while maximizing project value. Let us apply the concepts covered in this chapter to a practical engineering example. Suppose a gas pipeline is operating at high pressure and low temperature while free water is present in the system. By plotting the operating conditions on a hydrate stability chart, we determine whether the system is vulnerable to hydrate formation. If the operating point lies within the hydrate stability region, mitigation measures must be implemented. Possible solutions include methanol injection, MEG injection, dehydration, heating, or operational adjustments. The key lesson is that hydrate management begins with risk assessment and proactive decision-making rather than reactive intervention. Let us consider a simplified dehydration design example. The design process begins with gas flow rate, operating pressure, temperature, and inlet water content. The engineer first determines the amount of water that must be removed to meet the required gas specification. Next, the glycol circulation rate is estimated based on the desired dehydration performance. The contactor tower and regeneration equipment are then sized to handle the expected operating conditions. Although detailed design is often performed using specialized software, the engineering workflow remains the same. The objective is to reliably achieve the target gas quality while minimizing cost and operational complexity. Even well-designed systems occasionally experience operational problems. Hydrate plugs may occur when operating conditions enter the hydrate stability region unexpectedly. High water content in the sales gas often indicates poor dehydration performance. Foaming inside the contactor can reduce mass transfer efficiency and increase glycol losses. Operators may also experience glycol carryover, contamination, or regeneration problems. Successful troubleshooting requires identifying the root cause rather than simply treating the symptom. Continuous monitoring and preventative maintenance remain the most effective strategies for reliable operation. This chapter has introduced the fundamentals of gas hydrates and gas dehydration. We learned that hydrates form when water, gas, pressure, and low temperature occur together. Preventing hydrate formation is significantly safer and more economical than removing hydrate plugs after they develop. Dehydration provides one of the most effective long-term solutions because it removes water from a system before problems occur. TEG dehydration remains the industry standard for most natural gas processing applications due to its reliability and cost-effectiveness. Most importantly, effective flow assurance is not simply about preventing operational issues. It is about protecting assets, maximizing production, and delivering long-term value throughout the life of the field.